Hello and welcome to Game Revolutions, the series where I take a Moon Patrol clone video game that I started writing in high school and I see if I can improve it now using knowledge that I have gained since then. It's the series that has taken YouTube by storm, with each episode racking up hundreds upon dozens of views. In the last episode, I investigated step by step the performance issue I ran into after adding joystick control back, which caused the scrolling to go slow and then fast and then slow and then fast and then slow and then fast. I highly recommend that if you plan to watch that episode, you watch it now before watching this one, because this one will ruin it for you and reveal all that the cause was, and you should instead enjoy the suspense and watch that one first. But if you don't want to watch that one ever, you can certainly watch this one now, and you will enjoy it just as much or as little as you would have otherwise had you not. So today I'm going to discuss the strategy that I came up with to do things a little differently so that the problem goes away, and we'll walk through the code and see how it works. As a very quick recap, last time I narrowed down the performance problem to how I was doing stack blasting. So it would depend on where my rotational offset started, whether it started in this group of bytes, this group of bytes, this group of bytes, or this. If it was on one of the two ends, then it would be faster because I would get to take advantage of in fact, three full 8-byte stack blasts in a row. So there were 2 in a row in the code, and then there was like another where I would do it without a fix-up, but it was kind of separate. But if I didn't have the rotational offset here or here, if it happened to be in the center, then there were more fix-ups. I couldn't do as much stack blasting in a row as I could in the other cases. And that was responsible for the extra 20 to 30 scanline difference in speed. So here is my idea. Rather than storing one buffer from which I rotate, I will store 2 buffers. And the second buffer will be rotated by 16 bytes. So now I take cases. If my rotational offset happens to be here or here, I'm good to go. In fact, I optimized the code to only work in the cases where the rotational offset was on one of the 2 ends. And I forced a full 3 octet stack blasts, 24 bytes of stack blasting in a row without fix-ups. So what happens if the rotational offset is here or here? Well, that's when I use the second buffer instead. If the rotational offset is here, that becomes the rightmost octet in the second buffer, and this becomes the leftmost octet in the second buffer. This leads to much simpler code because I don't have to deal with how to handle the case when I'm in the middle. Instead, I just turn it into a case where I'm actually on the end. We're going to take a look at the code, but first let's take a look at the difference. So the red is the old code, the yellow is the new code. The yellow is significantly shorter. I've eliminated so many special cases and ifs and what about that and what about that, and that led to something much smaller. I always get a warm fuzzy if a new version of a project is somehow smaller than the old version. That usually indicates that I'm on a good track. This is what the most important part, the meat of the stack blasting code looks like now. The stack blasting is separated into 3 different rectangles, and I do all of them for each row, which means by the time I'm done with row 1, I've done all 3 pieces. By the time I'm done with row 2, I've done all 3 pieces. This already is different than what I had before. Before, I would do a whole slice all the rows, and then I would do another whole slice all the rows. And as you're going to see, doing it this way allows me to gain something. But first off, the very first rectangle, since we're doing stack blasting, that will show up at the far right end, and the last rectangle will show up at the very leftmost end. So if we started with this third rectangle, that's where we started the offset, and then we go just to the end of the octet. So this is just going to be a handful of bytes. And so I use self-modifying code to stack blast those bytes. And then what shows up on the right-hand side is whatever was in the octet until the rotational offset. Again, just a handful of bytes. The beautiful part is the part in the middle, which is 3 full uninterrupted octets. 24 beautiful bytes blasted in a row with no fix-ups. The other beautiful thing to point out are what fix-ups we do have to do. S is the register that points into the source buffer, and U is the register that points into the destination buffer, so that's the screen. Between the 3 rectangles, S might need a fix-up, and so we might do a little bit of this, and a little bit of that. And when we're done with a row, we do a little bit of this. But U does not need any fix-ups at all. So U is going to start at the end of the screen region where the background shows up, and it's going to continually move left every time we do a push. And that is all we're going to do to U. We're not going to readjust it depending on what octet we finished and blah, blah, blah. It just keeps gliding from right to left. S is the only register that needs fix-ups, and the fix-ups are very short. There is some conditional code that asks whether the rotational offset is in the leftmost or in the rightmost octet, and in some cases the fix-ups will be different. But that's it. Basically, all of this is the stack blasting code, and that's all. Before this is all the initialization, and they deal with cases where the rectangles on the ends are empty or non-empty. They figure out how many bytes need to be blasted within the partial octet stack blasting. Those are the first and the third rectangles. And it sets up the self-modifying code so that once we get into the loop, we don't need to check that anymore. So all of this code has already been told which of those 2 source buffers to use. That means the code that calls the stack blasting routine does have extra work to do, but it only happens once per frame, not once per row or twice per row, just once per frame. I take a look at the rotational offset and I just take cases. If it's bigger than hex 18, that must be the 4th octet from the left. If it's not, but it's bigger than hex 10, that means it's the 3rd one. Otherwise, bigger than 8 is the 2nd one. Otherwise, it must be the 1st one. And so these are my 4 cases, and they're the ones that set whether CR is left is 0 or 1. And they decide whether we're using my buffer number 1 or my buffer number 2. I then have similar code to deal with rotating the top row of the ground, and that continues to follow the same thing that the background rotation does. In a minute, we're going to run the code so we can see it in action and compare it to how it was doing before. But lest you think that I came up with that code perfectly on the first shot, first, what we're going to do is show a montage of all of the interim builds before I got to the one that worked. They will contain all of my fails. Now that the code appears to work, let's add back some of the stuff we'd commented out. So let's add back the joystick routine, and let's add back the parallax so that the mountains rotate only once every 3 frames. We'll run it in MAME this time so that we can also use the debugger to See if it's doing the right thing. See how the performance is. Okay, so the mountains are slower as they're supposed to be. The ground is still moving at that very fast pace. And it seems to be a consistent speed. No slow down, no speed up, no slow down, no speed up. Okay, so now it's really time to find out what we have gained. Once again, we will set our breakpoint here just before the sync. That tells us how far down the frame we got by the time we were ready to exchange the buffers. And hopefully it will be not nearly as far down as it has been before. 3E79. I'm going to ignore the first couple times and then take a look at where we're at. So beam Y is 137. Let's take a look here. 6, 6, 7, 6, 6, 8. 127. 128. 120, not back to 37. So before we seem to have about a 20 to 30 scanline difference. Now we're having about a 10 scanline difference, but not as pronounced. And we do seem to be not too far down. Before we were between 170 something and 190 something, and now we seem to be pretty solidly at either 127 or 137. And remember, that was with the joystick routine commented out. When the joystick routine was getting called, we were well past V-blank and we were using up an extra frame. So this is actually way faster than before. I did a little debugging, and it seems that the reason sometimes we're 10 scan lines quicker is that sometimes Rect 1 or Rect 3 is empty. This happens when the rotational offset is at the very beginning of Rect 1 or at the very beginning of Rect 3. In those cases, this jump, rather than jumping to a partial stack blasting routine to do a handful of bytes, just jumps down here to the next thing. And same here with Rect 3. It's not quite as consistent as I wanted it to be, but I think it is a little more consistent. I think the slow versus the fast is less pronounced. And overall, everything is much faster. So I'm going to call it a victory. I mean, if I really wanted to, I could intentionally blow some cycles here rather than jumping over. I could jump to some other routine that simulated how much time it would take to stack blast 3 bytes or so. But no, I don't want to do that. Now I could stop here. I have much faster code and much more consistently performant code than I did before. But if I get free advice that seems easy enough to try, how am I going to ignore that? So in the next episode, I will explore a comment from one of you and see if it can help. Until then, thanks as always for watching.